Weird. It's not like telling you, it's 200 calories per serving. How many calories are in each serving?
Mhm.
Have you tried 250?
I did, and it said that that was incorrect.
I'll give you any other information.
Yeah, that's why I was kind of confused. I wasn't sure if it was just the system or I was just getting it wrong, but I only had one attempt left.
Oh, okay. I think I see what it is now. Because it says that you have, what your is this 250 calories?
Uh-huh.
Nutritional calorie. And that says one nutritional calories equal to 1 kilocalorie. So what you have to do is convert it to kilocalories and then go from kilocalories to calories.
Got it. Okay.
Right?
Yep. So yeah, food calorie is just one.
I see. I thought I was like calories are calories, but then I realized the
Capital
C.
C calorie.
Yeah.
Small C calorie. Yep.
Okay, okay. So is the answer going to be in kilocalories or it's just regular calories?
Oh yeah, you need the answer is going to be in just calories.
And lowercase calories.
Yeah, lowercase calories.
Got it.
Science calories.
At first I was like, what? And then I reread the question. I was like, oh yeah.
So would it be 0.25 calories? Or that's kilocalories?
Yeah, that's kilocalories.
Okay.
That's got kilocalories.
So what do I convert it from the kilocalories? It's just supposed to go back to regular calories?
If it's okay, so the conversion for calories. Okay, so let's see if I can. So one capital calorie is going to be equal to 1 kilocalorie.
Okay.
So, and you're converting from kilocalories to 1 smaller case calorie, right? So if I have 1 gram, if I have 1 kilogram, how many grams would that be?
1,000.
1,000. So if I have 1 kilocalorie, how many small calories would that be?
1,000 calories.
Okay. In other words, you need to multiply that 250.0 times 1,000.
Got it. So would it be 250,000?
Correct.
Got it. Okay. Thank you. Thank you.
I was going to say you also may want to put in scientific notation to make sure you have the right.
Okay. Got it.
Okay. Any other questions? How about some cash? Nobody have any cash for me? Yes. Okay, so for Harnell and Fireball, which I don't think we have either. Well, we have Harnell on the screen, but Harnell, you guys won't have class on Friday. It's a holiday. And all you guys know that there's no class on Fridays, it's a holiday. There's also no class on Monday. You You get a 4-day weekend. Okay, there's also won't be any class on Thursday for Harnell for your labs. So there's no lab on Thursday. So I've been thinking about your exam, and I'm gonna be pushing it back by 1 week. So you're not gonna get your practice exam opening up tonight. It's actually gonna be opening up probably on Sunday. And then it's not gonna be due next Saturday. I'm gonna push it back just a little bit. Okay? That is correct, Yolanda, no lab on Thursday. So that's right, Michelle, no lab on Thursday. No lab on Thursday or Friday. Oh, don't cry, you know, dry those tears. How's everybody week going? How was your Valentine's Day? Did your booze buy you nice gifts? No?
Oh, yeah.
Oh, did you just see her shake her head? She's like, no, that bum.
So our exam is when?
Your exam is gonna be due not this Saturday, not next Saturday.
So March 4th?
So, yes, actually, no, I'm gonna have it be due in the middle of the week, so it'll be due on the March 1st. Okay, the reason why is because I wanna make sure that we cover everything, and because of the way the holidays are falling, we're gonna miss, some people are gonna miss parts of it, some people are gonna miss another part of it, and also since tomorrow.
There's a practice one will open up on this Sunday, right?
But you'll have, yes, so we'll have plenty of time to go over it. There will also be reviews. There are multiple reviews that will be going on. You wanna talk about that?
Okay, guys, so you guys know you have like 5 tutors for this class, and we all wanted to come together sometime next week to have like a tutoring session over everything you guys are going over, and we're thinking about Tuesday. Does that work for most of you? Tuesday and around the afternoon, at around like after 4-ish.
So will it be via Zoom as well?
I think we could,
Okay,
it's gonna be in message. We can set that?
Yeah.
Yeah, okay, then if it doesn't, just as long as you guys are free. If not, we can totally just like, since it's been pushed back a week, we can totally like work around whatever works best for you guys. But right now we're thinking Tuesday. Does that work for most of you? It work?
At 5.
About Thursday? Thursdays too?
Thursday should be good.
Thursday? Okay. Yeah, tutors, but Tuesday, Thursday?
and you'll share that link with me so that I can share it with everybody.
Yeah.
Yeah.
So don't forget.
And if not, you guys can just like email one of us and just tell us, and we can try to shift some stuff around to work for most of you. All right, because you guys, we still have 2 weeks. We were just hoping to get you guys ready.
There's a lot of people missing them.
Oh, so you tried, so my link didn't work for Angela yet. Is that what you're telling me, Michelle?
It was asking for enter the meeting number.
Okay, so I'll get those meeting numbers for you. Okay,
Okay, and then is Haley, she's not available by Zoom. She didn't have any Zoom contact information.
I will be putting up a Zoom contact information. I just got it, so I'll be putting that up tonight. So I'll try to get that to you as soon as I can. And I know that she's actually planning to have one day that she's gonna be on campus, and I'll let you know that day as well too. Thanks. So again, if things like that happen, just shoot me a text message so I can try to make sure I get that fixed. Okay, you guys ready to get started? You okay if we finish a little bit early, like when we finish this lecture, you guys okay if we take off a little early? If that's okay.
Yes.
Yeah. Okay, so I believe we left off on chemical reactions. Did we talk about chemical reactions? Or did we go beyond this?
Yeah.
We got beyond this?
I'm not sure. Hold on. I know we talked about it.
Okay, are we ready? Are we ready? I want to hear about Carolina later on. Tell Carolina I have her do my later on. Okay, now, you guys ready to get started? Okay, so last we left off, it was on chemical reactions. Yes, no?
Yeah.
Okay, so we've talked about sucrose. You guys remember the chemical formula for sucrose? You guys write that down? Yeah, glucose, so we need to do sucrose. So if we're talking about sucrose, let's talk about the chemical formula for sucrose. Now you're gonna have to excuse my third grade handwriting. So sucrose has a chemical formula of C12, H22, O21. I'm sorry, not O21, O11, I'm making stuff up. And this line, what does that line mean again? It's the yield, yes, but it means that we have a reaction. And so the sucrose is part of the, is that reactant or products? Sucrose. It is the reactant, that is correct. Okay, so for this chemical reaction, we have the production of carbon and water. Carbon and water are going to be my products. Okay, is it balanced? Okay, how would I go about balancing it?
12 in front of the C,
So in front of the C,
11 in front of, 11 in front of the H. And
Okay.
11 in front of the O.
is it 11 in front of the O? Because isn't H2O water?
Oh, just kidding,
That's-
no, yeah, just kidding.
Okay, so we want to make sure not to separate, them, right? They have to be together. Good job. Okay, so if we do verification. So we have 12 carbons on our reactant side, 12 on our product side. We have 22 hydrogens, and then 11 times 2, that's going to be 22 as well. And then we have 11 oxygens on our reactant side, and then 11 times 1, that'd be 11. So, good job. Okay, so we know that this is a balanced chemical equation. So what is one way that I can tell that a chemical reaction has occurred? So let's take a look at the sugar. How do I know a chemical reaction has occurred? In the case of the sugar, and then the case of what happened on the other side.
It turned black and started to probably smell really bad.
Yes, it turned black and it probably smelled really bad. Can I get sugar back from my charcoal that I've made at the end? No, I can't, right? So one way of determining whether it's a physical reaction or a chemical reaction is to determine whether or not I can get the substances back, or if I can separate those substances. Right? So in this case, I can't. So then I know that this would be a chemical reaction. It has chemical properties, right? So here are 3 scenarios. Very first one is wood burning on a fire. Is that a chemical reaction or a physical reaction? Wood burning on a fire.
This is important. Is it chemical?
So those who say it's a chemical reaction, raise your hand. Everybody has to vote. Online, you can raise your hand. Everybody got to vote. How many of you guys think it's a chemical reaction? Okay. Good. Okay, so the correct answer for A is a chemical reaction. Because we know we can't get that piece of wood back. It's ash. You can't get that ash and burn it again. Okay. What about an icicle melting?
Can't get it back.
You can't get it back. An icicle, you can. I'm asking, can you get it back?
Yes.
I mean, yeah.
So if I collected that water and then I froze it again, can I get the icicle back? So, physical reaction,
Yeah, so physical, you get back and chemical reaction.
that's correct. A glow stick, glowing. So after you crack it, is that a chemical or is that a physical? Chemical. Those who think it's a chemical, raise your hand. Remember, everybody votes. Those who think it's a physical, it is a chemical reaction. Okay, so pure substances and mixtures. So it's considered to be a pure substance is if all of the sample consists of one kind of matter. So for instance, if we just have water, H2O, it's considered to be a pure substance, right? If I just have carbon, it's considered to be a pure substance. If I have water and carbon, that's going to be considered to be a mixture. Okay, so a mixture is consisting of two or more pure substances. So how many of you guys drink sodas? Okay, so is a substance a mixture or a pure substance? So is the soda this substance? Is a soda a mixture or a pure substance? It's been a long day. It is a mixture. It is a mixture. Okay. So when we talk about mixtures, there are two types of mixtures. So one is called homogeneous. Homogeneous basically means that the substance that we're looking at, the mixture that we're looking at, looks uniform throughout, meaning it looks exactly the same throughout. So that would be homogeneous. I'll type that in for you guys. Right. Yep. Okay. And then the other one is heterogeneous. So that basically means that your mixture doesn't look the same. So when I was a kid, my parents were pretty poor. So we went out to eat only when it was like really big holidays or if something big happened, like somebody got a new job or something like that. So the place that I like to go to eat was like Denny's. And at that point, Denny's used to have the salt shakers, and they also used to have the little thing that contained sugar, right? And so I would love to sit there and take the salt and pour it into the sugar, right? And then, put it on somebody else's table, right? And then see what happens, right? Now, have you guys seen salt and sugar? Is that a homogeneous mixture or is that a heterogeneous mixture? It's homogeneous, right? Exactly the same. It looks the same throughout, exactly. So you can't tell the difference, right? You can't tell the difference by looking at it, but you can tell by tasting it, right? So homogeneous, when we talk about homogeneous mixture, it's only what we see visually, right? What we see, okay? So if I have salt and pepper and I mix those together, is that a homogeneous mixture? Nope. It's a heterogeneous, right? Okay. So you guys see the difference between the two? Easy. Yep. Okay. Now let's talk about some hard things. What about rum and coke? So if I have a rum and coke, is that going to be homogeneous or heterogeneous?
Is rum dark?
It's the heterogeneous.
Wait, you said you have
Why they look
Rum and
like?
coke. Rum and Coke.
Oh, they're, yeah, they're.
Rum and Coke, like the drink, cocktail. It's homogeneous. Okay,
I keep wanting to say it a different way.
homogeneous.
Yeah. wanting to
Yeah.
say it.
That's fine. I mean, it's homogeneous is the way that you.
Homogeneous.
Homogeneous. Homogeneous is easy to remember.
Yes.
Can we say that? It's a homogeneous,
Homogeneous.
that was the Coke is homogeneous because Coke doesn't like.
So you would say it's homogeneous because when we put them together, they all look like Coke, right? Yeah, so then, yeah, so that's what you're saying, yes. Yes.
Other Cokes and then this Coke is the same.
Yes.
Okay.
Although rum
I
and
know how to say
Coke are
this,
not
not
two Cokes.
that.
Rum is alcohol, and Coke is.
Oh, I didn't know, see how it was.
Okay, well, now you know that rum and Coke are not, yeah, not the same, yeah, not two different Cokes. Yes. Yeah, so, somebody had asked, is it okay if I say
That's how I get it.
homogeneous? Yeah, so that term homo means what? That's
Same.
prefix. It means the same. So we often think of homosexual, right? So that basically means the same sex, where hetero means different sex, right? So if we say heterosexual, that's different sexual. So we use a lot of these prefixes throughout science. And so it's good if you can sit there and use things that we are familiar with to help us remember what's going on, right? Okay. So now the thing about when we're working with mixtures can affect how things behave, right? It can affect the physical characteristics. So for instance, water boils at 100 degrees Celsius, right? You guys know that for sure here in Columbia because we spent a long time boiling water last week, right? Okay, so now, how many of you guys cook? Anybody cook?
Yeah.
Okay, I got one, two, three. Okay, I got yours. I didn't ask if you were good at it, okay? Now, how many of you guys have cooked pasta? You guys, I mean, and Harnell, any of you guys cook pasta? Okay, yeah, okay, good. So we can all relate to this, okay? So now, when you're cooking pasta, you add salt to your water. Not salt to your pasta, you add salt to the water first. Why? Okay, somebody says to add flavor. That's one thought. It does add flavor. I won't argue with you there. Oh, okay, wait. Okay, I'm getting a couple things here. I heard speed up the temperature, right? You saw that. You were also saying it. You said lower the boiling point. Okay, so you said lower the boiling point. We'll talk about that here in a minute. Okay, and then it says so it doesn't get sticky. It doesn't stick together. Okay, and somebody says bring the boiling point higher. Okay. So
Like lower than melting temperature of water.
So you guys are, so both of you guys are kind of close. So Mia is actually correct in this in terms of bringing the boiling point higher, right? So water typically boils at 100 degrees Celsius, right? So if you add salt to it, it actually brings up the boiling point by, depends on how much salt you add. The more salt you add, the higher you can bring up the boiling point. So that basically means water won't boil until it's like 105 or 110. So depending on how much salt you add to the situation. So what is the benefit of doing that? Somebody said something that kind of adds to this. You get the pasta hotter, it cooks faster, and it doesn't get sticky and soggy, right? Have you guys ever ate soggy pasta? Yeah, first, I have to say I have several times, right? Last meal, don't want to go out and buy anything, you know? Yeah, so the reason why we add it is so that the boiling point actually would be higher, okay? And it makes the water hotter, it boils the pasta faster, and the pasta doesn't stick together and get all soggy. So that's the reason why. and it adds flavor. Because salt makes everything taste better. Right? That's why I have high blood pressure, right? Anyway. So this basically is just showing us that, right? So this is our solution or our mixture of salt and water. And this is just our water down here. So water, when it gets to 100 degrees, that's where its boiling point set. And then our solution, you can kind of see it continuously go up because we have something there to kind of keep it together. Okay, and we'll get more into that physical aspects of things. It's going to play a part in us understanding how chemicals are going to behave together. Okay. Okay, so here we have pure bromine. Here we have pure water. And so this is showing you at a molecular level what these guys look like. Now, if I add a small amount of bromine to water, is it homogeneous? Is it a mixture? Is it pure? Okay. If I have a lot of bromine added to water, is it homogeneous? It's different. So are you looking at it here, right? Does it look different throughout that solution? Because remember, it's visually how we determine whether it's homogeneous or heterogeneous.
You have more rum than water.
So in this case, more bromine than water. Yeah, if I'm adding more bromine than water, doesn't it still look exactly the same throughout?
Right.
Yeah. Yeah, and if we're talking about rum, it works the same way, right? More rum than water. But in the case of rum, it depends on the rum that we have. We have
Wait. For rum, it looks like water is clear.
it's clear. Yeah.
Okay, yeah, same.
Homogeneous. Yeah, that's right.
So the first one with the small amount is homogeneous.
Yes, it's homogeneous. That's right. Okay, so it doesn't matter the quantity that we have. It just matters what it looks like visually, right? Homogeneous and heterogeneous is a visual characteristic, right? So we're visually characterizing that solution. Okay, and it only applies to a solution, right? Meaning that or a mixture, right? So if something is pure, it's not going to be homogeneous. Does that make sense? Because there's nothing that's being mixed. Okay, so if I said I have 100% ethanol, right? Is that pure?
Yes.
Is it homogeneous?
No.
Homo is the same.
Homo means the same, but it means it looks the same, right? But the question is, if I told you I have 100% ethanol, right? Is it pure? The question is, I asked you if it's pure. And everybody said, yes, that is correct. It is pure because it's 100%, right? And then I asked you, I said, is it homogeneous? No. Why is it not homogeneous?
Because it's 100%.
Because it's a pure substance. It's not a mixture. Only if it's a mixture. If it's two things that are coming together that are different, it's a mixture, right? Does that make sense? Yeah. And I mean, it's semantics. It's those little things, right? And those are those little things that they always get you on those test questions that you have to take when you're, becoming a nurse, or those little things that they go for, right? So I want to make sure that you guys understand that. Okay, so homogeneous basically means that it looks uniform. It's the same throughout the appearance. Okay. And then the properties of it, if we're putting them together, the physical properties are going to be the same throughout the entire mixture. Right. So if I take a little bit here and I take a little bit here, it's going to behave the same. Okay. And then heterogeneous basically means that it's non-uniform. Okay, so here we have pure water. Here we have pure ethanol. Okay. Is the pure water homogeneous? Is it pure?
No.
Okay. What about the ethanol?
It is.
If it's pure ethanol, is it homogeneous?
Oh, I know.
No. No, so that should be no. So the notes are wrong. That's what I'm getting at. And it also says there, because again, when we talk about homogeneous, we're making reference to so cross that out, say wrong, right? You're making reference to the physical appearance of mixtures, right? It should say that the sample is pure if you have it pure substance, right? Okay, so if I have a mixture of water and ethanol, is that homogeneous?
Yes.
Yes, it should be.
Okay, so if I have iron, how many of you guys eat cornflakes? Cornflakes? Okay. So have you guys ever did the experiment where you take your cornflakes, crush them up, like and then run a magnet over it?
Yep.
Yeah.
I've seen it.
You've seen it? Okay, so if you ever get a chance, and you want to waste a box of cornflakes, you have a strong magnet, you do that. Okay, so if we have a mixture of iron and sulfur, we can use characteristics, physical characteristics to separate the two. So we know that iron is magnetic, meaning that it's attracted to magnets. Okay, just like iron is attracted to magnets. That's not that. It is attracted to magnets. So I can use that to separate from sulfur because sulfur isn't. Okay, because sulfur isn't a metal. Care less about the magnet. Okay, so by running a magnet over that iron and sulfur, I can collect all of the iron. Make sense? So I can use physical properties to separate mixtures of things. Okay. So going back to the alcohol and water. So when you're making alcohol, on an average, if you have a really good system set up, you make about 20 to 25% alcohol. Okay. So how do I get from 20 to 25% alcohol to 100% alcohol? Distillation. So the process of distillation is separating it again on a physical property. In this case, the physical property is the boiling point. The boiling point of alcohol is lower than the boiling point of water. So then if I boil at 89.7 degrees, I can get alcohol and the water will stay down because water boils at 100 degrees. Okay, do you guys understand? You see? Okay, so we can separate mixtures by physical properties such as distillation. We can also separate by other properties such as filtration. So like, how many guys make coffee? The old way, the old school way, not the Keurig. No, all you guys
Grinder and all that.
Yeah, well, you don't have to grind it yourself, but you get grind beans and you put it in a filter, right?
Yeah.
Okay, and then you pour water through. Do your coffee grinds go into your? Why not? Because of the filter, right? So the filter is separating our coffee from our coffee beans, right? And so that's the process of filtration. So in your Keurig, you basically, whether you recognize it or not, it has a filter paper that keeps those grinds, hopefully, keeps those grinds from falling into your coffee, right? Okay, so here's an example of a distillation column. So you guys can see down here, right? So this is the liquid that we're distilling. So this is our mixture that we're starting out with. So we boil it. As we boil it, the mixture that has the lower boiling point, it's going to actually rise up. It'll flow through here, and then it'll continue flowing through here. So we're using a cooling system that cools the tube. So the cooling system comes in, it cools this tube. So it cools down the gas so that it becomes a liquid again. And it condenses. And then we get our liquid that we're trying to cover. Okay. So this tube is called a condenser. This here is called a distillation flask. So, like our coffee, here we have a funnel. This here is the filter paper. So we have a mixture that has solid particles and liquid particles in it. And so then we pour it through that funnel with the filter. We let gravity basically filter it out. It's called gravitational filtration. And we end up with our homogeneous liquid. And then all of our solids are going to be on top. You guys are going to do quite a bit of this. Okay, so then this brings us to types of pure substances. So we have what we call an element. So you guys are familiar with the elements. Your elements are in your periodic table. So can you guys name me a couple elements? Name me an element. You said iron. Say iron?
Yeah.
Okay, iron. You name me an element.
Phosphorus.
Phosphorus. Name me an element. Gold. Gold. Okay, what about you guys in Hardell? Give me an element. Michelle, can you give me an element?
Calcium.
Calcium. Oh, I like that. Calcium. Oxygen. Okay. Okay, so we're familiar with what elements are. Now, elements can't be decomposed into anything except themselves. They're just what they are. Oxygen is always just going to be oxygen, right? So a pure substance is only a single, a pure element is only a single element. It's that single type of element. It can be multiples of it, but it's only that type of element, okay? A compound can be broken down into two or more substances. So if we have water, H2O is an example of a compound, right? Because it has hydrogen and oxygen, okay? Carbon dioxide, a compound. Sodium bicarbonate, a compound, okay? So elements, compounds, okay? I'm gonna add one more, molecule. Okay, a compound is two or more different elements that are combined, okay? A molecule is two or more atoms. Okay. Okay. Where a compound is two or more different, a molecule is two or more, okay? So if I have O2, is that a molecule? Yes, because it's two or more atoms. Because there's two of them, right? Is it a compound? No. Because they're not different. They're both oxygen. Is it an element? Yes. Because it's all exactly the same. Okay. So we know that this guy is a molecule and an element. Okay, what about NaCO3? Is it an element?
Molecule.
Molecule? It's a molecule. Is it a compound?
Yes.
Compound. Okay. What about S8? Is it an element?
Element.
Element, okay, so it's element. Is it a compound?
No. Molecule.
Molecule, okay. Okay, simple, not too bad. So a mixture is impure. It can be separated by physical means. Okay, so when we separate it, we can end up with compounds and or elements. A compound is pure. Okay, it can only be separated by chemical means into elements and other compounds. Okay, so if I told you I have pure cane sugar from Hawaii, okay, is that a mixture?
No.
Is it a compound?
Compound.
Is it a molecule?
Mm.
That's right. It is a molecule. Okay. If I told you I had Molly. Molly is a drug, and it's often a drug that's too much information. that we add different other drugs to make it, right? So depending on the different drug you make it with, it will be a different color and will have a different effect. Okay, so is that a mixture?
Yes.
Yes.
Yes, it is a mixture. Is it a compound?
No.
We know that it's impure. Is it pure or impure?
Impure.
Impure. I keep giving you guys the answers. Okay, so if I have a vodka tonic, is that a mixture?
What?
A vodka tonic, vodka and tonic water.
Yes.
Oh, yes.
It's a mixture. Okay, is it homogeneous? Yes. Okay, if I have Kool-Aid, okay, so we can all relate to Kool-Aid. Okay, so if I have Kool-Aid, is that a mixture? Or is it a
Mixture.
compound? It's a mixture. Is it homogeneous or heterogeneous?
Homogeneous, because it looks the same.
It's homogeneous because it looks the same. That's right.
The whole thing looks the same.
Yeah, if you looked at Kool-Aid, doesn't it look exactly the same throughout the entire thing? It's all red.
You put powder in the water, so you gotta change the color.
Yeah.
Yeah, everything looks exactly the same,
So
right?
target said you got blue Kool-Aid, and you put the water in there, it's still gonna be blue Kool-Aid.
Yeah, okay. Okay, so here are examples of elements and compounds. So like your pencil, the pencil lead in your pencil, that's, even though somebody thinks it's lead, it's not really lead, it's graphite. Graphite is all carbon, right? So it's just C, right? Okay, you said iron. We have our iron bolts here. We have, although our pennies are alloys now, they used to be all copper, they're not anymore. What about those gold earrings that you wanted, pining for? What about lead weights, fishing weights, really lead weights? Okay, silver bracelets, the Wonder Woman bracelets. Okay, so those are all examples of elements. And then we have examples of compounds. Baking soda, right? Compound. We have chalk, an example of compound. It's funny how they have like 4 anti-acids on there. Rolaids, compound. We have lye, which is sodium hydroxide. All of these are examples of compounds. Water. Or maybe that's alcohol. I don't know. Might be either way. Okay. Okay. You guys are already familiar with how to use the symbols, right? Very familiar with it. You know that it's either 1 or 2. You know that if it's capital, right? It's capital and then a lowercase, we need to make sure it's capital and a lowercase. let's give us some examples. So I want to make sure that everybody understands this. Are these all the same elements? Okay. The first one, what? It's two atoms of different things. So we have, what is capital P? Phosphorus, yes. And then the O, oxygen. So we call this guy phosphorus oxide or phosphorus monoxide. Okay. Now, if you have a capital P and a lowercase o, like here. Polonium, that's correct. This guy is polonium. Now, polonium is radioactive. Phosphorus oxide is a poison, right? Now, neither of them you really want to play with, but the thing is like one is like it's radioactive, right? You know, you'd be like, maybe not so much, right? And let's say you were doing an experiment that required you to use phosphorus monoxide, and somebody gives you polonium. Yes, totally two different types of PPE. And you can only just imagine what type of reaction you're going to end up with, right? If you're adding polonium where you're supposed to be adding phosphorus monoxide, right? So it's important that we write things appropriately. Don't be lazy. You want to make sure you write it correctly. If you guys use lowercase p, you know, this means minus the log concentration of oxygen. That's what that is, right? It means something entirely different. So it's important that we write what we're trying to write. Okay, so how we write our elements are going to be very important. Okay, questions? Okay, so if we take a look at our periodic table, everybody has a periodic table? Question. $250 first.
Oh my gosh, how can you hear?
I'm gonna make my list by the time
I was gonna buy binders, like, binders, my pocket is full.
take it with me. While I get submitted. All right. Okay. So let's go to P table. Okay, you guys can all see the periodic table. So at the very top, you have these numbers up here. You guys remember what those numbers are called? I heard somebody say it. Groups, okay? That's right. These are your groups. And then on the side, these numbers are called periods. Okay, so we have groups up top, we have the periods on the side. So I want you guys to tell me the element that is in group 10, period 6. Group 10,
Titanium?
period 6. Platinum.
Oh.
PT, right? Yeah, everybody sees it? PT, platinum, okay. Now, when I was in college, and some places, some periodic tables that are kind of dated, they had what we call the main group. Main group consisted of groups 1, 2, 13, 14, 15, 16, 17, and 18. They would pretty much ignore what we call the transitional metals, right? Because those groups are easier to work with because of the octet rule, right? And the main group, they would say it would be labeled 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A, right? Yeah, so if you guys look at an old periodic table, they'll have them broken up into the main group and then what we call the minor group. These guys down here would be a minor group, okay? Now, today we don't do that. So, but sometimes the questions that you guys will have will ask you about a main group, right? But they'll also just give you a group. It'll say give you the group and it will give you the main group. So let me give you an example. So you'll see something like 13. So we group 13 / 3A. Okay, so that basically means that if we're in group 13 / 3A and period 2, that would be, so all you're going to look at is group 13. Who's in group 13? And period 2.
Aluminium? Or
So-
no,
Could be boron, right?
boron.
13 and then period 2. That 3A makes reference to that main group. So this here would be your 1A. This here would be your 2A. This here would be your 3A. Okay? You guys have that look. For those who I can see. Okay, so the main group, okay, so those that are in red, right? You see the ones, you see my little writing in red? Everybody sees this? What's my writing in red? Red? That looks bright. Oh. Okay, so this guy would be 4A, 5A, 6A, 7A, and 8A. Okay, so that would be your main group, right? And again, those were the ones, they were easily recognized by the octet rule. And we'll be talking about the octet rule a little bit later. But for right now, you just need to know that that's the main group. Now, there's no distinction between the main group and just the groups. Yes.
Okay, so if the upper 3 periods are A's, the 4 and below are the B's?
No. A's just make reference to the columns. So this whole column would be 3A.
Oh, okay.
Does that make sense?
So does that red middle section, is that B or is that the?
This here, this section right here. Yes, so these are your transitional metals, and yes, this would be your Bs. They would have Bs associated, right? If we broke them up into a main group and a minor group.
So that would be minor.
A represents the main group, and B would represent the minor. Yes, so your transitional metals, these columns down here would represent your minor group. But the minor groups were always minor. We never talked too much about them. We mainly talked about the main group. That's when I was in chemistry, right? Now, you guys are learning more than what we learned, right? We talk about it, we learn how to use them and how to do nomenclature, right? We did too, but usually it took us, that would be like our third, we did the quarter system. Third quarter, we would learn that, where you guys are learning it first semester. Okay, so let's say I wanted you to find the element that is in the period 6, group 14. Lead, that is correct. Okay, so period 6, group 14. Okay, so we use these groups and periods to help us find things, right? We also use what we call atomic numbers. This here is the atomic number. So if I make reference to atomic number 51, what am I talking about? Answer me, yes. Okay, so 51. Yeah, it's so atomic numbers and the groups and periods help us navigate the periodic table. The other thing that we want to know about those groups and periods, those elements that are in the same groups, for the most part, are going to have characteristics that are going to be the same. Maybe not all characteristics, but there's something about them that is going to be the same. So for instance, if we take a look at group 1 metals, group 1 metals are these guys. Hydrogen is not a metal, hydrogen is a non-metal. Okay, now all of these guys in group 1, these are called alkali metals. Okay, alkali metals are going to be more reactive than alkaline metals. Alkali metals are going to be more reactive than most metals on the periodic table. So these guys are very volatile, they're very reactive. Okay, and we'll talk about why that's the case. Okay, they behave very similarly. That group does. So if you're in the same group, you're going to behave similarly. Right? So you got a cousin? Jeremy? You do? What about you, Carol? You got a cousin? CE Carol, Escoda? That's cool. Yes, okay. Do you behave like your cousins? Do you guys both behave like your cousins? No. Are there any characteristics that you guys?
A little bit.
A little bit, okay. No, you don't? Okay, so you're messing up my point. Okay.
Yes, a lot.
Yeah, okay, better, yes, okay. So typically, if you guys are like within the same family, we all have dark hair, right? We all have dark eyes, right? You have some characteristic that you guys share, right? So these metals or these elements that are in the same groups are going to have similar characteristics, okay? So they're going to be characteristics that they share. They won't be exactly alike, but they're going to be characteristics that are alike. They can be substituted for each other sometimes, right? Pretty efficiently. Some of them may be more reactive than others, but they're going to react, you know. Okay. Okay. So since we're talking about elements, we've talked about compounds. Now I need to talk to you guys about the 7 diatomic elements. Before I forget about it. So there are 7 diatomic elements.
Sorry to interrupt. If we would this class last till 10 p.m.?
Yes, it normally lasts till 10 p.m., but we may get out early today.
Okay. By when do you think you will be able to upload this lecture?
It usually won't be uploaded until Sunday-ish, Sunday morning.
Okay. Yeah.
But I'll see if I can get it done earlier. Okay, you guys see my writing there? Have no fear of ice cold beer. Okay, you have 7 diatomic elements. There are 7 diatomic elements. Are hydrogen, nitrogen, oxygen, fluorine. chlorine, bromine, and iodine. Okay, so have no fear, have hydrogen. So it's hydrogen is always going to be written as H2 when it's by itself. So when we're talking about hydrogen gas, it's always written as H2. Okay. Nitrogen, when it's by itself, it's always going to be written as N2. Oxygen, when it's by itself, it's always going to be written as O2. Fluorine, when it's written by itself, it's always written as F2. Chlorine, when it's written by itself, it's written as C2. And bromine, when it's written by itself, it's written as Br2. And then iodine, when it's written by itself, it's I2. A mnemonic that you can try to remember is have no fear of ice cold beer, right? Have meaning hydrogen, no meaning nitrogen, fear meaning fluorine, of oxygen, ice, iodine, cold, chlorine, beer, bromine. All 7. Okay. Or another way of looking at it is you have this guy makes a 7 plus the hydrogen. Okay. So it's important for us to know that these molecules, when they're by themselves, are going to be diatomic. So they're diatomic elements. Questions? No questions?
So iodine is just gonna be.
Iodine,
Sorry, iodine, so it means the letter I and 2.
I2. I, capital I, 2, having 2 of them.
And then same thing for bromine, it's gonna be capital B, lowercase r and 2.
Yep. So when we're talking about bromine gas, right? Somebody says, we're working with bromine gas. So the symbol would be Br2. Yes.
So like without the 2 there, it wouldn't be hydrogen?
No, without the 2, it would be a hydrogen atom, which is different than hydrogen gas. Do you understand?
Yes.
To be the element it needs to.
That's right, because it's a diatomic element. That's right. Good question. So di meaning 2, atom, diatomic, 2 atoms. Okay, now we have 2 other elements that are polyatomic. Okay, the polyatomic elements are going to be, right down the room, so throw my little notes here. They're going to be sulfur 8 and phosphorus 4. Okay, so these 2 are polyatomic, meaning that they have more than 1 or more than 2. So when we make reference to phosphorus, and you're just talking about phosphorus, it should be P4. Although you will see mistakes made in the books, in your text, and then also in life. And then that's the same thing with the sulfur. It should be sulfur 8. Yeah, that look.
I was just waiting for you to do a little circle.
Oh, on the periodic table. Put it in a different color.
I'm good, you're good.
I'll put it in a box. Okay. There's only 2. Okay. Questions? we've already talked about what the subscript means because you guys are already balancing chemical equations. So you guys already know that that means 2 hydrogens. And if there's nothing by it, that means 1 oxygen. Don't you like it when everything starts to become reviewed? Okay. So we often make reference to an atom or a molecule. We've already talked about the difference between molecules and atoms. Okay, so the law of definite composition, or it's also called the law of constant composition. So the rate ratio between an element is going to be fixed. So for instance, if we have CO and we have CO2. So these are 2 different compounds. This one is called carbon monoxide. This one is called carbon dioxide. So the fact that we have 1 carbon, 1 oxygen here, and we have 1 carbon and 2 oxygen, these guys are going to behave differently. They have different effects on organisms or on us. So carbon monoxide, right, is a poison to us. Small amounts of carbon monoxide or enough amount of carbon monoxide with no ventilation will kill you. Where small amounts of carbon dioxide, it isn't going to kill you. But if you only had carbon dioxide, then it's going to kill you. But they will behave differently, okay? And so they're 2 different compounds. Their mass is going to be different, right? Because we have 1 carbon, 1 oxygen here. We have 1 carbon, we have 2 oxygens. But if I scale up, I have 50 carbon dioxides. That ratio is still going to be the mass between my carbon and my oxygen is still going to be the same. The ratio between the 2. I just have 50 of them. Okay. So the composition is always going to be the same, CO2. The composition of carbon monoxide is always going to be the same, CO. They're not the same. Does that make sense?
No, can you explain that a bit one more time?
Sure. So if we take a look at these 2 molecules, we have carbon monoxide. Carbon monoxide is composed of just carbon and 1 oxygen. Carbon dioxide is composed of 1 carbon and 2 oxygen.
Mhm.
So the mass of carbon monoxide and carbon dioxide are going to be 2 different, right? But my ratio of carbon monoxide, let's say I have 50 carbon monoxide, 50 CO. My ratio of my carbon to my oxygen is always going to be the same, whether I have 1 or if I have 50.
Okay, yes.
And so, and then my ratio between my carbon dioxide is always going to be the same, whether I have 1 or if I have 100 or 50, still going to be the same. These 2 are 2 different compounds. They behave, right? They have different effects, right? They're going to react differently, right? So I can't use carbon monoxide for something that I'm planning to use carbon dioxide for.
Okay.
That makes sense? So for instance, let's say photosynthesis, because we use carbon dioxide for photosynthesis. If I substitute carbon monoxide, it's not going to have the same effect that the carbon dioxide does. The reaction is going to be a different reaction. Most likely it's going to kill the plant. Okay.
Okay.
So even though that they have the same elements, that ratio is going to be important. Okay. Okay, so in chemistry, we do a lot dealing with charges. I think we kind of talked about this, that attraction. Yeah. So positive and negative charges. So what we call these guys electrostatic forces. So electrostatic forces make reference to the forces of attraction and repulsion, right? So if two things are the same, if I have two positive things coming together, what's going to happen? They're going to repel each other, right? If I have two negative things coming together, what's going to happen? They're going to repel each other. If I have something that's positive and negative coming together, they're going to attract, right? Okay, and that kind of makes sense in the real world. You have two negative people hanging out with each other all the time. It's horrible, right? Have you ever seen two negative people get together? Oh my gosh, fight, argue the whole time. It's the worst thing ever, right? If you have two positive people that get together, worst thing ever too. Oh my God, I can't see so much, I can't handle it, right? It's not gonna work. But if they're opposites, they balance each other out. They double each other out, okay? So here's an experiment that's done to kind of show this. So if you have a silk cloth, and you rub a glass rod, and then you touch it. So basically what you're going to be doing, you're going to be leaving a positive charge, okay? Then if you leaving a positive charge on the rod. So if you take the silk cloth, you rub it, you leave a positive charge on the rod. Now, if I take that rod and then I touch a ball, then that ball is going to become attracted to it. So that probably means, what about that ball if it's attracted to it? So I know my rod is positive. It's negative. Okay. So then if I transfer that negative to that, and then I transfer, let's say, then I take that. So if I do that to each one, and I transfer each one a positive charge, then two positive charge, they're going to repel from each other, right? And so that's what you see in this middle picture. Okay. So if I take a fur and then I rub it against a rubber rod, so then the electrons are going to transfer from the fur to the rod, making a negatively charged. So in this case, one of my pitch balls were positive. Now the other one is negative. Now they come together. We already talked about chemical reactions. You guys already know what the reactants and the products are. Are there any questions? We talked about coefficients. We've talked about how to balance chemical equations. Because I already done chapter 8 there, right? Energy. So definition of energy is going to be the energy to do work or to transfer heat. So if we do a chemical reaction and the reaction releases energy into the surroundings, so it's energy is exiting, right? So then that's called an exothermic reaction. So this is an example, butane burning. We actually release energy, so then that would be exothermic. An endothermic reaction is when we're adding energy into a reaction. So an example of that is photosynthesis. We have carbon dioxide plus water plus energy. It's going to make sugar. So glucose, 6H12O6, and oxygen. Okay. So this will be an example of an endothermic reaction. So in this case, the sun is providing that energy to sit there and make glucose and oxygen. So energy is being put into the chemical equation. Okay, you have that look. Questions?
So after how you got sugar, so why does the hydrogen stay on the left side? After,
How does, say it one more time?
I'm sorry, so after the arrow, I don't know if the certain vocabulary is, how you can sit on the left side,
What do you mean by stays on the left side?
like after it stays there, so the right side, give it. No?
Yeah, I'm a little, so wait. So when you're making reference to hydrogen, right?
Right,
Because remember, this is water, right?
right.
Okay,
Oh,
And then-
never mind.
okay. You're good?
Yeah.
Okay. Okay, yes.
So if this were put on a test, the word energy would be on one of the sides, and then we would have to determine whether it's exothermic or endothermic.
Something along those lines, yes.
Okay.
And we're gonna be more specific. Right now, we're just being vague about it. Don't worry about it. We'll be more specific about energy
When?
in a minute.
Oh.
Just relax.
Okay, energy.
Okay. Okay, so here is that example that I just gave you, right? Photosynthesis. Now, let me go back. Kinetic energy. Kinetic energy. Do you have any kinesis majors? Excellent. Okay, so you guys know kinesis meaning, what does kinesis mean? Movement, right? So kinetic basically means the energy associated with movement, right? So the energy due to motion, energy due to movement, okay? Potential energy is the energy that is due to the arrangement of the particles, right? So, for instance, let's say we had a person who's standing on a cliff, right? Now, at the top of that cliff, they have the highest potential energy that they could possibly have because they're just standing, right? That's their potential energy, right? As soon as they jump off that cliff, that starts to become what? Kinetic energy, because they're moving, right? Aren't they falling down to the earth, right? As they jump off the cliff, right? Their highest kinetic energy will be right at impact. As soon as they hit, that's going to be the most energy because you're going from a position or an arrangement down to total movement, right? So as you're shifting down, you're changing from your potential to your kinetic. You guys understand that? Okay. So if we think about this, right? Potential at the very top of the cliff, all they had was potential. There was no movement, there was nothing. It was just potential. So that will let us know how much kinetic energy they're going to have at the very end when they have no potential and it's all kinetic. Okay? So what's happening to that energy as they jump off that cliff? It's what? Is it expanding? Is the energy expanding? Are you somehow getting some magic energy somewhere?
Like building up.
What was that?
Building up. Like when you drop something, you like builds up mass.
So is it really building up?
I say it's like going.
So you say it's going down. What's going down? Is it all energy going down, or is it just a type of energy?
A type of energy.
Okay, so a type of energy is going down. Okay, so kinetic energy. So initially, all we had was potential energy. So we had 100% potential energy, right, at the top. So let me make a drawing. Okay, I'm doing a mistake here, so don't make fun of me. Not an artist. Johnny's at the top of the cliff. Okay, so at the top of the cliff, he has what we call potential energy. It's 100% potential. And then here's the bottom of the cliff. Okay, at the bottom of the cliff, when Johnny hits the bottom of the cliff, he has 100% kinetic energy. and 0% potential energy. I should probably say 0% potential energy up here. I mean, kinetic energy up here. Now, potential energy is a function of where Johnny's height is at. Johnny is at whatever feet he's at, okay? It's a function of that. If Johnny came down and jumped from here, he's not gonna have the same amount of potential energy that he had up here. As Johnny goes down this mountain, falling down the mountain, his potential energy is changing. So what's happening to that energy? That potential energy. Okay, so his potential energy is decreasing. Then what must be happening to my kinetic energy?
Increasing.
It's increasing, right? Okay, so that basically tells us a couple of things. It tells us one major things, right? Energy is conserved, right? And this is where we're kind of getting to. Energy is conserved. So energy can change its form. So I can go from potential energy to kinetic energy, or I can go from chemical energy to kinetic energy, okay? It can change its form, but at the end of the day, it's conserved. So if I had 100% potential energy, right? Then midway up the mountain, his potential energy should be what? 50%, and then his kinetic energy should be what? It should also be 50%. Because energy is conserved, right? And then when I get down to the bottom, it's going to be 100%. Okay, so in chemistry, these are the laws. Law of conservation. Conservation of mass. Mass is always conserved. Conservation of energy. Energy is always conserved. Okay, so now mass and energy equivalency. Okay, so if we take a look, Einstein basically said that E equals mc squared, right? So where E represents energy, M represents mass, C represents the speed of light. He later broke it down to just say E equals 1/2 the mass times velocity, where velocity represents velocity, speed, okay, square. Okay. Now, when you get in physics, they'll give you a difference between speed and velocity. We're not going to do that here. We'll let you say that for physics. Okay. Okay. So now I want you guys to think about this. The heavier light. This is heavier light. Fine. Okay, wait. Okay, we'll do it like this. Okay, is this lighter than this? Okay. So I have a coffee cup and I have a cap, like to a bottle. Okay. So I have my coffee cup that's metal and everything like that. Okay. Let's say I decide I'm going to throw my coffee cup at what? Perfect. Lauren. Gonna throw my coffee cup at Lauren. Ready? Oh, God. Okay. So if I decide to throw my coffee cup at Lauren, and I decide to throw the cap at Lauren, right? First day I just throw the cap at Lauren. You know, Lauren made me mad at throw the cap at her. Next day, Lauren made me mad at throw the cap at her again, right? Now I throw them at the same speed. Which one is going to have more energy? Or are they going to have the same energy?
it's heavier.
because its mass is greater, right? So energy is going to increase with mass. Okay. So let's say I have my coffee cup and my cap. Now I throw my cap 100 times greater than my coffee cup. Faster, not greater, faster than my coffee cup. Which one's going to have more energy? Guess it kind of depends.
Is the cap way up?
We'll say that the cap weighs 100 times less than
Yeah,
coffee
that's-
cups, yeah. So we'll say that the cap weighs about 50 times less than a coffee. Okay. So which one is going to have more energy? You said the cap, right? Because in that case, again, energy is increasing with what? Velocity. Okay, so energy is directly proportional to velocity. Now, is mass and velocity directly proportional, or are they indirectly proportional? They're inversely proportional. Right. Okay. So things to keep in mind when we're doing problems, right? Write stuff in. Okay, so you guys want to take a say 10-minute break? 10-minute break. You want to keep going? Let's take a 10-minute. Give everybody a chance to stretch your legs. 10-minute break. We're going to try to get out early today because we're almost done, right? How many more slides do we have? 20. Yeah. Yeah, they'll go fast. So a 10-minute break. I'll see everybody here in a minute. Come back.
So, Dr. Henry, quick question.
Yes.
Would you be extending the lab report?
Yes, so you guys could have a couple more days to get the lab reports in.
Okay, also just to confirm, we are not gonna have class Friday the 17th, this Friday?
That's right. No class on Friday.
Okay, thank you.
Yeah, if you show, you're gonna be there by yourself.
Is work canceled?
We'll work on Friday. Yes. They're
Oh, okay. You want me to just put them back?
Dr. Henry.
they really do. Everything at rice cake is small. Good question.
I'm sure that they got that. Okay. You guys are all like,
Do some chips. So,
salt and liquid.
steak is gonna do that.
Really?
It's a rabbit food.
It looks like it's for my.
Oh.
I have to.
Oh, so I can't do that.
How's it going? How's it going? How was your Valentine's Day?
Dr. Henry,
Yes.
do we have a lab report for density?
Yes, you have a lab report for density. You need to upload it.
Okay, just upload the one that we did during class, correct?
Yes.
Well, we don't have to do like a whole report, just like the mentals?
No, the Mentos, you're gonna have 3 formal lab reports. The Mentos is the first one. Your second one, I have to remember which one it is. It's, I think it's copper chemistry.
Okay, but you will let us know as we go, correct?
Yeah, you'll know.
Okay, perfect. Thank
It'll
you.
have to be a Formal lab report. You only have 3 of them to do, so.
Okay, thank you.
Yeah, technically you have formal lab reports this Friday. The instructions on how to do it is online. So you can watch the video, it'll take you step by step through the process. Depends how well you are at following the instructions.
Zoom meeting?
So Zoom meeting on Saturday, I mean on Sunday. Yeah.
Oh, well, what time?
Yeah, 3 hours. And then you guys come.
Dr. Henry,
That's Norma.
is the Mentos lab due this weekend or when is it due?
So for Kalinga, yours is due this weekend. So I may extend it to everyone till Sunday. Yes, Sunday at 11:59 p.m. If you have questions, you can come to the 30. I mean, cocktail hour, not the 30. Sorry, another thing.
You're gonna be out of town and still have cocktail hour.
Yeah, because I'm gonna definitely have my cocktail at that point. My cocktail day, because I realized that I can't do it during the week. My sister had cocktails last night. I had one drink, and today I was struggling. You should ask my 1B class. It was a rough. I only had one. Well, I was up really late too, and I had one. So, yeah.
What about, what was it, lab 3 that we were doing last time, the one with the little computers and stuff?
So, yeah, you guys need to finish that, right?
Yes.
So what I'm gonna have you guys do, we can't do it next week because we don't have class on Monday. You guys know there's no class on Monday? No class on Monday or Friday, this Friday or Monday. Holidays. So, next part. We'll try to squeeze it in. We'll try to finish maybe a little bit early, and then anybody who needs to finish up that lab, can finish it up on Wednesday. Yeah, the
Okay.
next lecture isn't. Okay, so let me read some of these messages.
Quick question. Dr. Henry.
Yes.
Why do they put phosphorus in food?
To kill things.
Really?
Yeah.
Is it-
So it's used, it's used as a preservative, right? So part of it is to keep certain things from surviving. They put levels that isn't gonna affect us, but they'll affect bacteria or affect.
Yeah, phosphorus is like, there's like actually like, not like a degree, like there's like certified nutritionists that like say they're like maybe more study into it with they studied from the educational college, that within the churches that degree, there's studies of phosphorus. And they did like. How is it? There's like bacteria, just- it's like bacteria you need for this. So it seems like some companies like measure it. And it's not.
Okay, so a recap. There will be no class on February 16, 17, and 20. Okay? So that would be Thursday, Friday, and Monday, no class. Okay? I will have my cocktail hours from 6 to 8 on Sunday. I am going to give you guys a little leeway this week. I will extend your lab reports, right? Extend them to, actually, I'll send them to Monday night at 11:59 p.m. Since, you know, if you're willing to sit there and do the work on your holiday, then that's you, right? So, and I'll also extend your homeworks till the homeworks that are due this Wednesday till 11:59 p.m. on Monday. Okay? And don't wait till 11:59 p.m. to try to do it on Monday, okay? Okay, you guys ready? Next part. Okay, so we've talked about the different phases. We went from, if we're going from a liquid to a gas, so that process is called evaporation. Okay. So now what's really happening in the case of evaporation is you have your liquid phase, you have your vapor phase, right? And so in a system, it takes energy for it to sit there and go from our liquid to vapor phase, right? You have to put energy to make that happen. Okay. Now, if we're not putting enough energy, what happens is that we get a point where they're trying to go with each other in both directions. So you have some that's going into your vapor phase and some that's going into your liquid phase. Okay. So you need to get to enough energy to cause that breakaway. Okay. And we're going to be talking about that breakaway in terms of energy. Okay. So if you take a look at this, because molecules in this case, we're using water as an example. Those molecules are interacting with each other, right? They have means of interacting with each other. And that's part of the reason why we also have to put that energy in to get that breakaway. Right? We can't think of the molecule being all by itself. It's acting in a group. They're going to be acting on each other. So do me a favor. Let's see. Let's do a little example. Let's see if we can get this to work out. So let's see. Gonna borrow you, 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 gonna borrow you. Okay. Yeah, come out here. Okay. And okay. Okay. So now. Perfect. Okay, so now what I want you guys to do is I want you guys to come hand in hand and get through here.
Like holding hands?
Not holding hands, just kind of like your hand in hand, like close, like lined up in order and get through here. No, as a group, I would guess, try to get through. So, okay, so the thing is, okay, so you guys see this, right? So they're reliant on each other.
We can't see what you guys are doing.
Okay, let me see, let me get my camera. Let me see if I can get the camera to work. Tell me if the camera's working.
Sorry.
You're good.
This is fun. We're having fun.
Oh, sorry, Chance, why don't you tell you?
Yeah, it was.
Okay.
He said go, we're going. We'll send her go send, man.
Like a separate tissue.
Let's go with this side.
Oh, no. Oh, boy. That's so cool.
And so, and, okay.
Oh,
Okay, there we go. Okay, so now what I want you guys to do, can you guys see now? Yes, wave to everybody, you know, okay. Okay, so you guys are gonna try to get through here, right? And I want you to kind of line up in a way to get through here, right? And you gotta be close together. You can't just, you know, you can't be far apart because you guys are, okay, keep going, keep going. Now you see that they all have to interact with a way to sit there and be able to get through here, right? So regardless of what they want to do, they had to interact with each other to make it through, right?
Yes.
Okay, so this here, each of them represents a different molecule. Every one of them represented a different molecule. They had interactions with each other where you're touching each other when you came through, right?
Yeah.
They had physical interactions with each other. That sounds dirty. I know. Get your minds up the gutter. Okay, so they had to physically interact with each other to make it through this process, right? Now, these are called intermolecular forces. Like, have you heard of the interstate, I-5?
Yep.
Okay. I-5 is an example because it's called interstate because it's between states, right? So between molecules, between each of them, they had to interact. You have the two that were in the front that were touching each other, the ones that were behind them that were touching the ones in front of them to try to make it through. Okay. Now, this is what you guys go ahead and sit down. I like you guys standing here, but this is what makes. I guess I should go in the middle now, right? So this is what makes molecules. They're different boiling temperatures. They're different boiling points, right? Depending on how many interactions that there are, right? You guys had quite a few interactions. Well, it was really close and tidy there, right? It was a struggle at first because when they first got through, they just kept knocking my chair out the way, my block here. But you know, but they were able to get through eventually. Okay, so when we talk about evaporation, we're actually looking at these interactions that are happening between those water molecules, right? These water molecules are interacting with each other. For them to get enough energy to break away, we have to put a lot of energy in. It took a lot of energy in there. Was it easy to get through? Was it easy to get through? Not the first time? The first time was a hot mess, right? You guys were just all out disarray, right? Yeah, and then, but you guys kind of got it order going on. You got it organized enough to sit there and get through. They had to break that threshold, okay? Now that threshold in science, we call enthalpy, right? We call it the heat of something, right? Enthalpy, and I'll type that out for you guys. Okay, now enthalpy is going to be energy that's going to be associated with so many amount of, do you guys remember what the mole is? Okay.
6.025 times 10 to the 6th power.
6.022.
Oh, 22
times 10 to the.
That's right, because it was on
to the 23rd. Yes. Okay. That's right. Okay. So, oops, got carried away. So enthalpy, and sometimes we'll call it the heat of, right? Enthalpy or the heat of. So the heat of vaporization is going to be the enthalpy of vaporization. So it's that amount of energy that it takes to change 1 mole of a liquid into vapor at a constant temperature. Okay. Now, our boiling point is going to be the temperature where vaporization can happen. So that's going to be our boiling point. And the thing is that those intermolecular forces, those guys interacting with each other, they're strong. But we need enough energy, we need enough heat, enough temperature to cause them to start separating, cause them the ability to break away. Okay. So here's water boiling. So this is what the vapor looks like. You have the molecules all by themselves. This is what liquid looks like, right? Where they're all kind of tied together and they're interacting with each other. So you need enough energy to sit there and help them break away. So in this case, to go from liquid to vapor, are we putting energy in or are we taking energy out? So if it's in, is it endothermic or exothermic? Endothermic. Okay, so if I'm going from a vapor to a liquid, am I putting energy in or am I taking energy out? Energy out. So is that going to be endothermic or exothermic? Okay, so this is just an example of boiling. It kind of gives you more of a visual of what boiling, what's happening when you're boiling. Now, the thing is that it's going to be in equilibrium until we're able to break free. Meaning that the molecules that are escaping are going to be equal to the molecules that are coming back into solution. Okay, until we put enough energy to cause it to shoot the other direction. Okay. So for a pure substance, Q represents heat. So that Q is going to be equal to our delta H vape, where that's the heat of vaporization or what we call the enthalpy of vaporization. And usually that's something that we can look up. It's given to us somewhere on a table. Or if we have that, the heat or the energy from that system, and we have a mass or number of moles, right? We can sit there and calculate that delta H as well too. So just by changing around the equation. Now, the heat of condensation is that the energy that's it takes to sit there and start condensing. Okay. Now, here's the beauty of it, is that the heat of condensation and the heat of vaporization should be the same. Only thing that's different will be the sign, meaning a positive and negative sign. Okay. So if we're putting energy into a system, if it's an endothermic reaction, then the energy that's being put in is going to be positive. If energy is being released from the system, then the energy that's being released is going to be negative. Okay, so in other words, if we had our chemical equation A plus B yields C plus energy. If energy is on the product side of the equation, your energy is going to have a negative value. So if we have A plus B plus energy, yields C, then your energy is going to have a positive value. So heat of fusion is the formation of a solid. So it's the energy that it takes to form a solid. The heat of vaporization is the energy that goes from a liquid to a gas. Okay. So in the case, these are different substances. See water here. Okay. Okay, so the melting temperature of water is 0 degrees, right? So ice starts to melt at 0 degrees. Okay. So the heat of fusion, so the heat to go from that ice to a liquid is going to be 333 joules per gram. Water boils at 100 degrees Celsius. So the heat of vaporization is going to be 2.26. Okay. You guys are probably saying, what the hell? So how can I use this? That's what it's going to be for. So to calculate our energy is going to be, again, represented as heat. So we're going to use Q. It's going to be equal to either mass times delta H, in this case, delta HT, for vaporization. Okay. So if our units are in mass, you're going to be using mass. If our units are in moles, we're going to be using moles. Okay. So it says how much energy is needed to vaporize 188 grams of a liquid if it has a heat of vaporization of 1.13 kilojoules per gram. So then, in other words, we're calculating Q. And we want energy, so units for energy are going to be joules or calories, capital C calories or lowercase c calories. Okay. So in this case, we're going to be using kilojoules, kJ. So in this situation, this is just multiplying these two values. So this here represents our delta H. So we go 1.13 kilojoules per gram. And then we're going to be multiplying that by 118. Mass is 118. Sorry, 188. By the way. Okay, so now I ask you guys some hard questions. See how much you guys remember from all the other lectures. How many sig figs should I have?
3.
So then my answer should be
12.
right there with you. Okay, pretty simple, right? Not too bad. Okay. Okay, so when we talk about fusion, right, the heat of fusion, so then that's going to be the amount of energy in freezing a sample, or in the case of solidifying a sample. So we're going from a solid to a liquid, or from a liquid to a solid, right? And so the only difference is going to be that sign again. They're going to be comparable to each other in terms of the value, but it's whether it's a positive or a negative sign. That's the difference. So it's gonna work exactly the same way. So you're gonna get Q equals delta H fuse times the mass or moles. So in this case, how much energy is required to melt 25.0 grams of ice at 0 degrees Celsius? Okay. So in this case, we'll go to that table that we saw earlier. We'll look for water. Okay, so the heat of fusion is 333 joules per gram. So then we're going to be using that. And here's the units that we're going to be using. So we have Q equals delta H plus M delta H plus. Okay, where M represents the mass, which was 25.0 grams. Then we're timing it by 333 joules per gram. Our grams are going to cancel out. And we're left with just so how many sig figs should I have? 3. So the answer is 8325 joules. So then my final answer should be 8.3. So now you know that this isn't a point, that's a comma. Right?
Oh, I
So-
think kilojoules.
Oh, you said kilojoules, 8.3 kilojoules. Okay. So should we round it or should we leave it alone? So it's exactly a 5. So then it should be 8.320. Or you said 8.32. So both of those would be correct. Yeah. Okay. Questions? Yes.
So like on the slides here, it says the answer is 8.33 kilojoules or,
Yeah, it's a typo.
okay,
So it should be, because we are exactly at 5. So if this guy was greater than 5, it would be 23. So just on the slides, cross it out.
but why did they make it kilojoules instead of leaving it a joule?
You could have left it a joule, it would have been fine, but you could also leave it in kilojoules. Because it's the same, it means the same, right?
Right. Or I'm like, why? If I don't have to do it.
Yeah. Okay, so the next thing that we're going to talk about is, it's called specific heat. Now, specific heat is, it's going to be used during the time when you're going from, like, say, one temperature to another temperature. So you overcome the hot. I'll show you a picture what I mean by that in a minute. So like in the case of, if you're going from one phase to the other phase, right? So remember I told you, you have a meet a threshold, and that's going to be your temperature, right? So your enthalpy is that threshold that you have to cross over. So when we talk about specific heat, it's when you're in a certain phase, right? So if you're already in the liquid phase, then you're going to be using that specific heat for the liquid phase. If you're in the gas phase, you're going to be using that specific heat for the gas phase. And then if you're talking about everything, then you're going to have to take into consideration both the specific heat and the enthalpy. Okay. So let me give you an example of that. So how much energy is required to change the temperature of 25 degrees of water from 10 degrees Celsius to 50 degrees Celsius? Okay, so water freezes at what temperature? 0. Water boils at what temperature? So if I'm between if I'm between 10 degrees Celsius to 50 degrees Celsius, which phase am I in? I'm in my liquid phase. So in this case, I'm going to go here. I'm going to go here. I'm going to look at my specific heat for the liquid phase of water, which is 4.18. Okay. And then these are the units right here. It's going to be joules per gram times Celsius. So you guys remember from the last, you know that the equation for this guy was Q equals MC delta T. Okay, where M represents the mass. C represents the specific heat. And delta T is going to be temperature final minus temperature initial. Okay, so if we go ahead and plug it in, we know that our specific heat for liquid it was 4.18, and that's joules over grams Celsius. Our mass, this is our mass. And then our delta T, that's going to be 50 minus . Okay, then we plug it all into the equation. So the Q equals 25 grams times our specific heat, which is 4.18 joules grams Celsius, times our change in temperature, which is 40.0 degrees C. So then cancel out our C's, we cancel our G's, and then we're left with just joules. So if we multiply across, and how many sig figs should we have? 3 sig figs. $4,180 joules. So there were a couple of questions that I didn't answer in the chat. So one of them was, what is KJ per? What's KJ per G? So this represents kilojoules, the energy per mass, right? So when we talk about our enthalpy, our delta H, that's going to be either in kilojoules per gram, or it's going to be kilojoules per mole. So it's just the units that we use for enthalpy. Okay. Questions? Good. Yes.
There's 3 sig figs. What does it mean? 118.
Okay, I'm going to ask you this. Right. So 418, is that equal 4,000?
No.
And 80? They're not, right? So remember, sig figs are just the numbers that we're sure about, right? Remember, you always have to keep replacement, right?
Mhm.
So if I paid you $4.18 and you were owed 4,018, is that the same thing? No, it's not. You'd be a little upset with me, right?
Okay,
You
I
got it.
remember it now. Forgot about the zero.
Yep. Remember, zeros are going to be used as placeholders. Okay. Any other questions? Yes.
Never mind.
You're going to ask me about the kilojoules and joules. They just
No, I was gonna ask you, we had to do like the significant figures, but I wrote it wrong, so I put F or 40 instead of with a point zero at the end.
Ah,
So we made it 3. I was like, wait, you gave me 2? But
Okay.
there's 3.
okay.
Yeah.
Okay. Now, sometimes we have to use the change in temperature, and we have to use the change in state. So remember those thresholds, those are going to represent your change in states. And then the change in temperatures are going from that one temperature to the other temperature. Okay. Sometimes we got to use both. And so you need to be aware of what's happening and when you're going to go through phase changes. So for instance, here, so this is called the temperature versus heat graph. Okay. So this here represents the heat and energy. This here represents the temperature. So this here represents, oops, from this point to this point, we're a solid, right? So this is below zero. Let's say if we're talking about water, this will be below 0 degrees, right? So this represents below 0 degrees if we were talking about water. Now, the melting or the fusion, this here, or the freezing or solidification, right? So this part represents that change in phase, okay? That threshold that we need to get over. So remember all those intermolecular forces, you have to put so much energy to release it, right? That's what we're talking about here. Okay. And so if you look at the equation, right? So for this part down here, you get Q equals the MCAT, right? And then when you're trying to go from a phase change, right? The hump to get over the phase change, that's going to be Q equals M times delta, in this case, delta fuge. Okay. And then when we get into liquid phase, we're in the liquid phase range, we're going to be using Q equals our MCAT. But in this case, we're going to be using the specific heat of liquid instead of the specific heat of ice. Okay. And then in this situation here, that's going to be going through a phase change, right from a liquid to a solid. You need that hump to go from a liquid to a solid. So then that's going to be Q equals M times delta delta H of A. And in the case of the gas, right? We're in the gas phase now, so we've gone over the hump. Then we're going to be using Q MCAT, but in this case, our heat capacity is going to be that of the gas. Okay. So you're asking me, now how do I use this, right? It's long. So calculate the total energy transferred when when 19.6 grams of ice initially at minus 12 degrees Celsius is heated to steam at 115 degrees Celsius. Okay. Okay, so we're gonna take these numbers and we're gonna pull them back to the other side. So like that little graph. You guys don't mind. Make my life a little bit easier. So we have this little graph, right? So we're starting at what temperature? So we're starting at negative 12. So negative 12 is where we're starting. Okay, degrees Celsius. And then we're going to 115?
Yep.
Okay, we're going to 115 degrees Celsius. I should probably use a different color.
I can see
You can see
Yeah,
the purple and the blue don't blend.
not at all. As I didn't know blue, I thought it was great.
Okay, now water freezes at what temperature? 0 degrees Celsius. So this point here is going to be our 0 degrees Celsius. Water boils at what temperature? 100 degrees. This is going to be 100 degrees. Okay, so when we do these calculations, we're going to go from our T final, in this case, for this first stage, would be our TF for our ice phase is going to be 0 degrees. And then our T initial is going to be 12 degrees, or I'm sorry, minus 12 degrees. Okay, so if we go, our delta T for that is going to be what? T final being 0 minus 12. You mind if I get all of our values for things, right? Because we know that the delta CCAT here is going to be 4.18 joules grams Celsius. I'm going to go pick up the other our other page quick. Top of my head. So our C for ice is 206, and our C for gas is 2.00. Also need our heat of fusion and our heat of vaporization. For water. Now we got everything that we need. Back to this. Okay. So if we go ahead and plug in our values here, we're going to have so Q is going to be equal to Q equal to the mass was 119.6. Correct me if I'm wrong. Tell me if you just throw things out there. That's correct. Times our capacity, our specific heat for ice, which is 2.06. And then that's joules per grams degree Celsius. And then we said the change in temperature was going to equal 12 times 12. So, and I'm just going to, for my case, I'm going to call this Q ice. So I know that it's for the ice. Okay, can you guys see that? So that's going to represent the very first one. So that's going to represent this stage right here. Okay. And then this here is that fusion, right? So it's that hump that we have to get over. So in that case, we're going to just multiply Q fuse. And then that's just going to be that 119. 19.6 grams times 333 joules per gram. So that's going to be our second column. So that's going to represent going from a solid to a liquid. Our third column is going to be just that liquid phase. So then that's going to be Q liquid. So Q lick. Again, the mass 19.6. That one's times 4.18 joules per gram Celsius. And then we need to change temperature. So here we're going from our final temperature is going to be 100. Our initial temperature is going to be 0. So then it's just going to be multiplied. I'm just going to put the full thing. 0. Okay, so then our fourth part is going to be the liquid gas column. So we're going from getting over that hump again. So in this case, we're going to use the delta H again. So then that would be, in this case, a vaporization. So we go vape equal to our mass, 19.6 grams times 2.26. This case is kilogram or kilojoules, right? Kilojoules per gram. Then the last case is going to be our Q gas. And that's going to equal 19.6 grams times 2.00 joules per gram Celsius. And then now we're going from our final temperature is going to be 115 minus 100. So if we go ahead and do that math here. How many sig figs should I have for this first problem, first one?
3.
3. So we get 480. That's joules. Okay, and then next, my Q plus. How many sig figs?
3.
3. So I get 6,530 joules. Next one. 19.6 times 4.18 times 100. So how many sig figs? 3. 8. 0 joules. Okay, now this one. 19.6 times 2.26. Now this is kilojoules, right? So ultimately we should change it to joules. We'll start off with joules, so it's like 44 point, so 3 sig figs, 44.3 kilojoules. gonna be equal to 44,300. Then my last one. 6 times 2.00 times 15. 5,880. So it's asking us for the total heat from the beginning to the end. So our Q total is going to be equal to Q ice plus Q use plus Q liquid plus Q vape plus Q gas. So we add them all together. $5,400. So all you did was take the parts for each of the different steps, but they have to be broken up into their steps. So you have to remember, you always need that threshold. That's going to be your enthalpy. Anytime you have that leveling off enthalpy, right? That threshold to get over. If it's a run, right? It's rising, right? So in that case, that's always going to be your specific heats. Enthalpy, your specific heats. Okay. Don't worry about it. I'll give you a couple of problems to work on. Okay. Questions? Concerns? Cash? You guys have that look? Brain dead yet? Okay. We're almost done. How many more slides? Three more slides. We're on the home stretch. Okay, so now Valentine's was last night, right? And all you guys look very tired. How many of you guys have booze? How many of you guys spent time with your Valentine yesterday? Okay. Obviously, some of you guys spent a lot more time than others because you can tell how tired you're looking right now, right? So I know that there's a lot of cuddling and snuggling and all that going on, right? Right? Yeah, okay, good. Okay, so this deals with that concept of transferring, right? That contact. Right? You guys made some contact last night, right? Okay, so one of you guys are cold and one of you guys are hot. Right? Are you hot or you're boo? Who's hot in your relationship?
Like, I'm cool.
You're cold?
Yeah.
Okay, so you put your cold feet on his back, right? Okay. So, and when that happens, what happened to you? Your feet warm up, and then what happens to him?
Like his back gets cold.
It gets a little bit colder, right? So what happens is that in the case of your feet are getting warmer, but his back is getting colder. They meet in that central temperature, right? And so a lot of times we're thinking about that heat transfer, that energy transfer. So if they're in contact with each other, they're going to reach a point of what we call equilibrium, or we call it thermal equilibrium. And that's what this is just basically showing us, right? So his heat is being transferred to your cold feet, right? And so you guys get to a point where you're both are exactly at the same temperature. He's a little pissed off because he's colder, and then you're a lot happier because you're warmer, right? It works out, okay? Definitely, right? So that's an example of the laws of conservation of energy. Because in that case, energy is being transferred from one individual to the other, right? And at the end of the day, if we added both of the energies up, they should be the same, okay? So that brings us to laws of conservation of mass. We talked about balancing chemical equations, an example of the law of conservation of mass. We talked about the laws of conservation of energy, that thermal curve that we just spent almost an hour doing on its own, right? And then her putting her feet on her boo's back, another example of law of conservation of energy, right? Okay, so at the end of the day, the things that we need to remember. So in chemical reactions and chemical changes, it's going to be conserved. So things are going to never be created, nor are they going to be destroyed. They can't just come up out of the blue. They have to start from something, right? And at the end of the day, what you started with, it should be in, right? It's never destroyed. It's changed in terms of its chemical arrangements, or it's changed in terms of the type of energy you're using, but it should always add up to be the same. Okay. So here's an example. My last example for the night. So we have gas, natural gas. Natural gas is a chemical, right? So we're burning that natural gas. That natural gas causes this boiler to boil the water. Water boils, we make steam. The steam turns the turbine. Okay? The turbine turns the generator. The generator generates electrical energy. Right? Electrical energy is then used for our lights, for our hot plates and our stoves, right? Our TV in the living room. So the thing is that at no point did we just magically make energy. It was just changed from different forms. We went from a chemical energy to boiling water. That'd be type of energy, which I think that would be thermal. Okay, so we'll say thermal, and then also should be the movement of that turbine, mechanical or kinetic, right? Movement, right? The generator making electrical energy, and then electrical energy being used to power our lights, our range, and our TV. So at the end of the day, it's concerned. This is all about chemistry. This is what chemistry is about. Okay, so officially welcome to chemistry. Right? Okay, that's it. I will see you guys on. Well, I'll see you guys on Wednesday, but I'll see some other ones on Tuesday. You guys have a good night. Go snuggle with your boobs.